want to do one more example before we move on to the next section of solving a differential equation by Laplace transforms. And I must admit this is a silly example because I could do this one by inspection. Y is going to be e to the kt. Any multiple of e to the kt, because I didn't give us an initial condition. Okay, but it's kind of nice when we learn a new system and it feels kind of crazy and wonky to use it and see that it actually does give the right answer. Okay. I also need to make one correction from the videos that I created on the partial fraction decomposition. I stated at one point that when you're solving for the unknown constants, you can't plug in complex numbers. You could. It would work. You could then solve for the unknown constants, which will be real numbers. Usually we use complex numbers because it makes our life easier. Plugging in complex numbers tends to just make the system of equations more complicated. So I don't recommend it, but I said you couldn't do it, and that wasn't true. So I do apologize for that. All right, so let's solve this using Laplace transforms. Okay, and this one is not an initial value problem, so I'm going to just have to use my initial condition, y of 0, as an arbitrary constant. Okay. All right, so I start by taking the Laplace transform of both sides. And of course here, that constant k can be factored out. Okay. Now on the left-hand side, I'm using rule 11 for our derivatives. So I'm just going to get, I'll come down here where I've got more space, s copies of the Laplace transform of y minus y of 0. Now, since I wasn't given an initial value, this is just my arbitrary constant. The arbitrary constant corresponds, in this case, to the y value at time 0. And that's equal to k times L of y. Okay. I think what I'm going to do is just swap these pieces so that I get a positive y of 0 over here. So I'm going to have s Laplace transform of y minus k Laplace transform at y is equal to y of 0. Okay, excellent. So here I can factor out the Laplace transform at y. It's being multiplied by s minus k, and that's equal to y of 0. So, solving for the Laplace transform of y, I'm going to get y of 0 over s minus k. Excellent. So, now I've solved for this. Notice once again, this was a differential equation. There was a derivative. This is an algebraic equation. There are no derivatives in here. Okay. All right, so let's take the inverse Laplace transform of both sides. So, of course, the inverse Laplace transform just undoes the Laplace transform, and that takes me back to y. I'm just going to write in that that's going to be my function of t. Of course, the Laplace transform of y, you can see, is a function of s. Remember, the variable changes here. Okay. Now here, this is just an arbitrary constant, so I can factor that out. And then we're taking the inverse Laplace transform of 1 over s minus k. Well, that's a match for this, where k is my a value, so I'm just going to get an exponential function. So we get y of t is equal to y of 0 e to the kt. Now, if you remember, we said we were supposed to get a multiple of e to the kt, and you can confirm that multiple must always be the initial condition, because if I plug in 0 for t, that's going to make this e to the 0, which is just 1. I should always be getting, whatever this constant is, it is the y value at 0. Okay, now in the next section, in 6.2, we're going to start to take a look at some differential equations where we actually need Laplace transforms. So the examples that we did in this section were just to get us familiar with the process. They were linear equations that we could solve. This was also separable, and we could do this one by inspection. So we had lots of techniques that were simpler than Laplace transforms. But we're going to move on to some equations where we actually do need to use Laplace transforms.